Okay, so in the last period, we have seen that two types of oscillators are there. One is the RC oscillators. RC oscillators. Oscillators are basically divided into two types. One is RC oscillator, and second one is LC oscillators. Okay. And the RC oscillators, again, they are further divided into two categories. One is phase shift oscillator. Phase shift oscillators. And second one is wine bridge oscillator. Wine bridge oscillators. Both are RC type, but their structures are slightly different. Okay, both are using R and C. Both are RC, but slightly the connection is different. Okay, LC oscillators are also again classified into two categories. One is Hartley oscillator. Hartley oscillator. And second one is Coolpix oscillator. Coolpix oscillator. Both are LC type of oscillator. Both are LC type. But slight change in the connection. So slight modification in the connection also results into a different type of oscillator. Okay. So as per our syllabus, we have to study only these four types. Okay. So we'll start with the LC oscillators first, and then we shall move on to RC oscillators. Okay. So I will discuss about the Hartley oscillator circuit. And after that, we'll go for Coolpix oscillator. After that, phase shift oscillator. And last one, bridge oscillator, wine bridge oscillator. That we are going to complete. So I think the sequence is now very clear. So let us start with the first one, that is Hartley oscillator. Hartley oscillator. Hartley is the name of the scientist who actually designed this oscillator. This is LC type. Hartley oscillator is of LC type. LC means inductor and capacitance, they are used. So as usual, now what is the basic condition for oscillation? You must have an amplifier, basic amplifier. All of you know, this is a basic amplifier. Then you must have a feedback network, that we know. In oscillators, we use positive feedback. What do you mean by positive feedback? The meaning of positive feedback is the feedback signal is in phase with the input signal. Okay, so there is no actually input. We are just passing on the output to the input. This is the way how the feedback is given in the oscillators. This is a positive feedback. And here you get the output. So this is the particular block diagram of your oscillator, any type of oscillator. It will have a basic amplifier, it will have a feedback network. Correct. Now, if this basic amplifier is a C amplifier, for example, common emitter amplifier, then as we know, if there is this is the input, then we get this type of output. That is 180 degrees phase shift is there. There is a 180 degrees phase shift. Okay. So what is the job of the feedback network? we want positive feedback. Positive feedback means the feedback signal must be in phase with the input signal. Okay, feedback signal must be in phase with the input signal. So this feedback network further provides 180 degrees phase shift to the output signal. So there is a total phase shift of 360 degrees. 180 degrees due to amplifier, and 180 degrees due to feedback network, due to the feedback network. Correct. So total phase shift of 360 degrees. So 360 degrees means 0 degrees. 0 degrees phase shift. So your input signal and feedback signal, they are in phase with each other. That is the meaning. But as we know, the feedback is very small. Only 1%, 2% feedback or 4% feedback is given. Last time I gave you the Barkhausen criteria. All of you know. What is Barkhausen criteria? Barkhausen criteria. We know the equation for feedback gain with feedback, AV. AVF is equal to AV upon 1 minus K times A, where K is positive. K is positive for positive feedback. For positive feedback. So oscillator is a case of positive feedback amplifier, as we know. Okay. Now, when K times AV, which is called as the loop gain, is nearly equal to 1, what will happen? If this factor becomes 1, it becomes 1 minus 1, that is 0. So AVF tend towards infinity or maximum value. And AVF tend towards infinity or maximum value. Okay, and when AVF tend towards the maximum value, the circuit starts oscillating. Okay, so it doesn't remain a positive feedback amplifier. It gets converted into an oscillator. Okay, now it doesn't require any input signal. The output signal itself becomes the input signal for the amplifier. And that's why the circuit starts oscillating. Okay, so positive feedback amplifier gets converted into an oscillator as soon as you reach this condition, K times AV approaching 1, means AVF tending towards maximum value, and that leads to the oscillations in the circuit. Okay, this is the basic criteria for oscillation. That we call it as the Barkhausen criteria. Now in the Hartley oscillator, whether it is a Hartley oscillator, Coolpix oscillator, phase shift oscillator, or Weinberg oscillator, whatever may be the type of oscillator you are using, everyone has to follow these rules. That is, it has to complete or comply with the Barkhausen criteria. It has to meet the Barkhausen criteria. So Barkhausen criteria is a general criteria for any oscillator, whatever may be the type of the oscillator. So now we start with the Hartley oscillator. So what is the basic diagram of Hartley oscillator? As we know, there is a basic amplifier. Just now I have drawn. This is a basic amplifier. And there is also a feedback network. This is the feedback network. Okay. This is the output of the basic amplifier. This is the input to the feedback network. This is the input to the feedback network. This is the output of the amplifier or oscillator, you can say. and this is fed back to the input, as we know. Is it clear now? This is basic amplifier, your basic amplifier. We call it as CA amplifier. This is the feedback network. Feedback network, in case of Hartley oscillator, it consists of two inductor coils. One is L1, another is L2, and one is C. That is a capacitor across a coil. And this point is grounded. So this is L1, this is L2, and this is C. Okay, so we feed the signal, output signal, this is output, VO dash. Okay, we feed that output as input to the feedback network. And here we get K times VO dash, which is a feedback signal, VF, which is the input signal, actually, Vin is equal to VF to the basic amplifier. So this feedback network not only feedbacks the signal, but also phase shifts it by 180 degrees. So there is a 180 degrees phase shift. If this is the signal, then you get this type of signal at the feedback output. Okay, so there is a 180 degrees phase shift. 180 degrees phase shift. So this is very important. Who gives this phase shift? It is by this feedback network. L1, L2, and C, they form a feedback network. Okay, so this is the basic block diagram of your Hartley oscillator. C amplifier, common emitter amplifier, works as a basic amplifier, provides the gain. Then feedback network consisting of L1, L2, and C. Correct. Now just change. If instead of L1, if I say C1, C2, if I say C1, C2, and across them I connect the inductor L. Okay, I just change this network. Instead of L1, L2, C, I change it to C1, C2, and L. As soon as I change these components, it becomes a Coolpix oscillator. So there is nothing different in that. It becomes a Coolpix oscillator. So what is the change in Hartley oscillator and Coolpix oscillator? Only the feedback network. Replace L1, L2 by C1, C2. Replace C by L. Okay, it becomes a Coolpix oscillator. So very simple to remember the difference between Hartley oscillator and Coolpix oscillator. Okay, both are LC. Both are using inductor and capacitors. Okay, except the change is instead of L1, L2, we are using C1 and C2 in case of Coolpix oscillator. Instead of C, we replace it by L. So that is the only difference between Hartley oscillator and Coolpix oscillator. So I think it will be very easy for me to discuss Coolpix oscillator after Hartley oscillator. Okay, so this is the basic block diagram of your Hartley oscillator. Now we will draw the actual circuit diagram of Hartley oscillator. I will draw this circuit. This is a common emitter amplifier, as we know. This is a basic amplifier. This is ground. This is RE. This is a bypass capacitor, CE. Okay. Now here, instead of RC, instead of collector resistance, we connect a coil. We call this coil as RFC coil. RFC means radio frequency coil. That is the inductor coil. Or it is also called as choke. Radio frequency choke. Okay. Then there is a, as usual, voltage divider network will be there. This is a voltage divider network consisting of R1 and R2. Okay. Now, this is the input and this is the output. Now, in between the input and the output, we have a feedback network. Here I connect an inductor L1, L2, and C. Connect this. This is your output. This is the feedback network. Okay. And this is the input. It's very easy to remember. Mhm. Okay. This is my feedback network. This is the feedback network. And this one is your basic amp. This one is your basic amp. This is your basic amp. Okay, so whatever block diagram we were drawing, same block diagram is we are following. This is your basic amplifier. This is the output of the basic amplifier. We are giving it to the feedback network. The output of the feedback network is given as the input to the basic amplifier. So these are the coupling capacitors. CC. Okay, so this is the basic diagram or circuit diagram of Hartley oscillator. Now here this point is grounded. So this becomes L1. This is your L1. This is L2, and this is C, capacitor C. Okay, as we know, when inductor and capacitor, they come in parallel, they form a tank circuit. In 12th standard, you must have studied. Correct. Whenever an inductor and capacitor comes in series, or comes in parallel, they form a tank circuit. This is inductor and this is capacitor. Okay, if you charge this capacitor C, okay, through some power supply, this is the battery, let us say. And here is the switch. Okay, when I turn on this switch, the capacitor will charge, correct? And when I turn off this switch, when I remove this switch, what remains is only correct. The capacitor is charged. What will happen? This capacitor will discharge through the inductor and it will recharge in opposite direction. This side will become negative, this side will become positive. Afterwards, again it will discharge from here to here. Now this side will become positive, this side becomes negative. So this continues. Discharging, charging, discharging of the capacitor through the inductor continues. And that forms a oscillations. So it looks like a oscillation. This is actually charging and discharging of the capacitor through the inductor. So here, instead of saying L, we call it as L1, L2. Actually, it is L. L means L1 plus L2. Very easy. L1 plus L2. L means L1 plus L2. Okay. So whenever we feed a signal to L1, there is a induced EMF, self-induced EMF in L2. Correct. आपल्याला माहिती इंडक्टरचं हेच आहे, प्रिन्सिपलच आहे की ज्यावेळेस इंडक्टन्स मधनं करंट फ्लो होतो त्यावेळेस सेल्फ इंड्युस्ड EMF तयार होतो त्याच्यामध्ये. आणि हा काय करतो? L2 ला इन्फ्लुएन्स करतो. मग L2 मध्ये अपोजिट व्होल्टेज तयार होतं. इथं जर L1 च्या अक्रॉस E1 व्होल्टेज तयार झालं तर L2 च्या अक्रॉस E2 व्होल्टेज तयार होतं, परंतु ते अपोजिट इन डायरेक्शन. हे जर इकडे पॉझिटिव्ह आणि इकडे निगेटिव्ह असेल तर हे इकडे निगेटिव्ह आणि इकडे पॉझिटिव्ह असेल. म्हणजेच इकडचं व्होल्टेज आणि इकडचं व्होल्टेज 180 डिग्रीज आउट ऑफ फेज येतं. इंड्युस्ड EMF इज 180 degrees out of phase with the input EMF. E1 हा input EMF आहे आणि E2 हा induced EMF आहे. L1 मुळे L2 मध्ये इंडक्टन्स induced EMF तयार होतो. But that is in opposite direction. Correct. So there is a 180 degrees phase shift automatically produced due to these inductances. Okay. So this signal, it becomes already this amplifier has provided 180 degrees phase shift. this inductance produces one more 180 degrees phase shift. So that becomes 360 degrees phase shift, and that is a positive feedback to the amplifier. Correct? So in this way, the oscillations start. Now the capacitor starts charging and discharging through these inductors, L1 and L2. Just now I have told you the tank circuit working or functioning. So in the same way, it will continue to charge and discharge through the capacitor, through the inductor. Okay, it will recharge in opposite direction. So this charging and discharging continues. Okay, and that we call it as the oscillations. So oscillations are maintained in the circuit. So this is nothing but the Hartley oscillator circuit. If you have any doubt, we know that what is the this is the circuit diagram. I will just wipe out that circuit diagram. We know that Xc means 1 upon 2 pi Fc. All of you know. What is Xc? Xc is the reactance of the capacitor. Similarly, XL, reactance of the inductor, is given as 1 upon 2 pi FL. Now, at resonance, Hartley oscillator मध्ये सुद्धा resonance तयार होतो. At resonance, Xc becomes equal to XL. म्हणजेच काय? 1 upon 2 pi Fc is equal to 1. Sorry. It's XL is not 1 upon 2 pi, it is 2 pi FL. It is 2 pi FL. Okay, so it becomes 2 pi FL. Now I will take this side, so it will become 1 is equal to 4 pi square F square LC. Okay, or this F square I can write F square is equal to 1 upon he and he term khali jail 1 upon 4 pi square LC, or F is equal to under root 1 upon 4 pi square LC. Now 4 pi square means 2 pi into 2 pi. 2 pi into 2 pi. That is 4 pi square. हे रूट मधनं बाहेर येऊ शकतो. बरोबर आहे का? म्हणजेच F is equal to किती येणार? F is equal to हे 1 म्हणजे 1 स्क्वेअर आहे. हे 1 पण बाहेर येईल. 1 upon 2 pi. रूट मधनं बाहेर आली की 2 pi होईल ते. आणि अंडर रूट LC. This becomes the formula for Hartley oscillator frequency. Okay, where फक्त इथं एकच आहे, where L is equal to L1 plus L2. हे लक्षात ठेवा. Where L is equal to L1 plus L2. आपण जे फीडबॅक नेटवर्क मध्ये L1 आणि L2 वापरलं होतं, त्या दोन्हीची ऍडिशन म्हणजे टोटल L. So this is the formula for Hartley oscillator. Okay. Now, what is the condition for feedback? Okay, or we can say condition for sustained oscillations. The oscillations कायम राहण्यासाठी, condition काय आहे त्याला? Condition for sustained oscillations. Your feedback K is given as L2 upon L1. हा feedback factor झाला. आपण मगाशी लिहिलं नव्हतं का K टाइम्स VO डॅश. हे K म्हणजे फीडबॅक फॅक्टर आहे. आउटपुट पैकी किती सिग्नल आपण इनपुटला फीडबॅक करणार आहे. तर हा फॅक्टर जो आहे फीडबॅक फॅक्टर हा L2/L1 एवढा फीडबॅक फॅक्टर. ओके, दॅट यू शुड रिमेंबर. अँड व्हॉट शुड बी द गेन. बेसिक एम्प्लिफायरचा गेन किती असायला पाहिजे. सो इट मस्ट बी ग्रेटर दॅन L1/L2. हा फीडबॅक फॅक्टर के आणि हा गेन एव्ही तुमच्या बेसिक एम्प्लिफायरचा गेन किती असायला पाहिजे. तर L1/L2 यांचा रेशिओ जेवढा येईल त्याच्यापेक्षा जास्त हा एव्ही असला पाहिजे. ह्या दोन कंडिशन्स जर सॅटिस्फाय होत असतील, फीडबॅक फॅक्टर, प्रॉपर फीडबॅक फॅक्टर, किती फीडबॅक द्यायचा आणि गेन, ह्या दोन कंडिशन जर प्रॉपरली सॅटिस्फाय झाले तर तुम्हाला ऑसिलेशन्स हार्टली ऑसिलेटर मध्ये मिळतील. अन्यथा ऑसिलेशन्स मिळणार नाहीत. ह्या दोन कंडिशन्स म्हणजेच बार्कॉशियन क्रायटेरिया शुड बी सॅटिस्फाईड. करेक्ट. बार्कॉशियन क्रायटेरिया जोपर्यंत सॅटिस्फाय होत नाही तोपर्यंत ऑसिलेशन्स मिळत नाहीत. बार्कॉशियन क्रायटेरिया काय, के टाइम्स एव्ही शुड बी ग्रेटर दॅन ऑर इक्वल टू 1. हा जोपर्यंत क्रायटेरिया सॅटिस्फाय करत नाही तुम्ही तोपर्यंत ऑसिलेशन्स, द पॉझिटिव्ह फीडबॅक एम्प्लिफायर डझंट गेट ट्रान्सफॉर्मड इनटू अन ऑसिलेटर. तोपर्यंत तो ऑसिलेटर म्हणून काम करू शकत नाही जोपर्यंत ही कंडिशन तुम्ही सॅटिस्फाय करत. ही कंडिशन सॅटिस्फाय करण्यासाठी के ची व्हॅल्यू किती असती तर L2/L1 आणि गेनची जो ट्रान्झिस्टर वापरलाय तुम्ही त्याचा व्होल्टेज गेन किती असायला पाहिजे तर L1/L2. ह्या दोन गोष्टी जर पाळल्या, व्यवस्थित सॅटिस्फाय केल्या तर बार्कॉशियन क्रायटेरिया सॅटिस्फाय होतो. आणि बार्कॉशियन क्रायटेरिया सॅटिस्फाय झाला की मग तुमचं जे सर्किट आहे ते ऑसिलेशन्स चालू करतं. म्हणजे तुम्हाला ऍक्च्युअली ऑसिलेशन्स दिसायला चालू होतं. अशा प्रकारे साइन वेव्ह ऑसिलेशन्स दिसायला चालू होतं. So this is the basic circuit theory behind your Hartley oscillator. So I will end my lecture here. Next time we will continue with the Coolpix oscillator. कुणाला काही डाऊट असेल तर विचारा. I will stop here.